It was one day in the summer of 1968. An air traffic problem had just occurred at Washington National Airport. Low-level clouds were blanketing the city when the Washington VOR went out. Approaches were to the south, and the low ceiling made use of the Georgetown ADF marginal. 8 planes were holding, preferring to wait for the Washington VOR to be put back in service. At the top of the stack was an Eastern DC-9, Flight 669. At the controls, veteran Eastern Captain Emil Glanz.
We had one big advantage over the 7 other aircraft in the stack below us. Our aircraft was equipped with area navigation gear that permits us to operate precisely outside of normal air route. The Washington controllers knew from our flight plan that we had RNAV gear on board. Eastern has been testing it along prescribed RNAV routes in the Northeast Corridor for some months. So we simply called approach control and asked for an RNAV approach to runway 18. They cleared us from the top of the stack right to Cabin John Bridge, down the river, and into the airport. We actually used the Georgetown ADF as our primary, but our area navigation equipment was tuned to the Baltimore VOR as a backup. We broke out right on course over Roosevelt Island and landed on runway 18 without any problem. All the other pilots in that stack were wondering how we could do it. Actually, it was easy with area navigation.
Area navigation is a precise method of navigating by cockpit instruments without actually overflying ground-based navigation aids. It is a method now used by some transoceanic carriers. The normal route from point A to point B is via the vortex. A pilot of an RNAV-equipped aircraft can plot a direct route. Locations of waypoints along the route are cranked into the onboard equipment. A computer performs the mathematics necessary to locate the waypoints. The pilot then merely uses an onboard RNAV display to fly from one point to the next, just as if he were flying directly to or from ground nav aids. In the case of Eastern Flight 669, the Cabin John Bridge became a waypoint. With its location entered into the onboard area navigation system, Captain Glanz could fly right to it. Then, with the approach end of runway 18 as a second waypoint, he could make his approach down the river directly toward Washington National. The emergence of airborne navigation equipment with this kind of flexibility is of great significance to air traffic controllers. Everyone knows that the ever-increasing growth of air traffic presents a mounting challenge to our present-day air traffic control system. The FAA is constantly working to upgrade the system, to take advantage of new technological advances, and to incorporate new, improved techniques of air traffic control. The ultimate purpose is to use the airspace more efficiently. NAS en route Stage A and the Advanced Radar Tracking System known as ARTS are important steps in this direction. Another important step is area navigation. Area navigation can help overcome the limitations of today's air route structure. At the present time, air routes funnel traffic directly to or from VORTAC ground facilities. This limits the configuration of the routes and the number of routes that can be established between points. It creates traffic congestion over the NavAid facilities. Even more important, since arrival and departure procedures are based on the same ground stations that serve the en route structure, there's always the problem of altitude changes in the most crowded areas.
Navy 17135, turn right heading 190, cleared 22 right ILS approach, you're 3 miles from the outer marker.
This has increased the workload on controllers. They must hand carry aircraft through the crowded areas. They must radar vector them in and out of terminals, around storms, and at all other times when deviation from standard airways is necessary. In effect, controllers have been required to navigate aircraft.
76 is 5 miles southwest of Newark. Roger, 15,000.
Of course, controllers have accepted this responsibility as basic to the success of the system, and they have been greatly successful in carrying it out. But radar vectoring is time-consuming. It requires considerable voice communication. It demands increased attention to the aircraft being vectored, greatly restricting the number of planes a controller can manage in a given situation. If the air traffic control system is to keep pace with the growing demands being placed on it, controllers must have some relief from this kind of procedure. Area navigation is one way this can be provided. The concept of area navigation is not new. Since the late 1940s, it has been the subject of tests and evaluation by equipment manufacturers, users of the airspace, and the government. It has long been considered an appropriate step toward more efficient utilization of the VOR DME network, a step that could be taken just as soon as area navigation equipment reached required levels of accuracy and reliability. Recent tests run by Eastern Airlines in the Northeast Corridor and by American and United Airlines between New York and Chicago confirm the results of exhaustive tests run by the FAA. Area navigation equipment has reached a level of accuracy equal to or exceeding present-day VOR DME navigation. This has prompted the issuance of FAA Advisory Circular 9045, providing guidelines for incorporating area navigation into the national airspace system. The circular spells out the 3 principal applications of area navigation. First, a new en route RNAV route structure that will be planned so flight distances and traffic congestion are reduced. Second, RNAV arrival and departure flight paths in terminal areas, including special paths for STOL and VTOL aircraft where feasible. And third, RNAV instrument approaches to runways without instrument approach capability. The purpose of this film report is to explain how these RNAV applications will be carried out and what they will mean to the controller. To begin, let's see how RNAV equipment permits accurate navigation from one point to another. There are several types of equipment, ranging from sophisticated, self-contained inertial guidance systems now being used by overseas carriers, to Doppler gear, such as that now in use by the military, to hyperbolic omnitrack equipment, and to relatively inexpensive airborne computers that function from VOR DME inputs. For the purpose of illustration, we will feature one typical RNAV unit, a VOR DME input type called VAC, for Vector Analog Computer. In its simplest form, this type of equipment can be used by the VFR pilot. Before takeoff, the pilot plotted his course from point A to point B. He selected waypoints along his intended route that are within range of VOR DME stations. Selecting these waypoints has the same effect as moving the station to a position more convenient to the pilot. He defines the location of each waypoint by distance and the radial from the station. He determines his track, and he knows the frequencies of the vortex. He tunes in the frequency of the station, sets his track, enters the radial and distance of the waypoint from the station, and turns the set on.
Queen Air 150, ready for takeoff.
Queen Air 150, cleared for takeoff.
Queen Air 150, roger.
It is unnecessary that the controller know what kind of equipment is installed in a given aircraft. The minimum standards of performance and accuracy are applicable for all types. The controller is interested chiefly in the capability of RNAV equipment, whatever the type, and how it affects air traffic control.
Run up 11, contact ground control now, 121.9. United 57, clear to land runway 19 right.
Right turn.
Queen Air 150, contact departure.
Right turn,
Queen Air 150, changing over. Good day.
With RNAV equipment, the computer establishes the relationship between the point selected and the VORTAC, and from then on uses the waypoints as its frame of reference. The pilot makes a control adjustment to line up the symbolic aircraft on the indicator with the vertical line, and he is on course to the waypoint. He can determine his distance away from the VORTAC whenever he wants. And his symbolic pictorial indicator tells him when he is getting close to the waypoint. As he gets close, a horizontal needle comes into view, each calibration representing 2, 1, or 10 miles, depending on the scale selected. 2 miles is usually used. When the needles cross the symbolic aircraft, the pilot knows he's directly over the waypoint. There's no cone of confusion as when flying directly over a nav aid ground station. With RNAV equipment, the pilot knows exactly where he is. He continues flying on the proper heading away from the waypoint. The equipment shown here has the capability of 2 waypoints. The pilot can enter the location of the next selected waypoint. Thus, he can leapfrog from waypoint to waypoint until he reaches his destination. This is a relatively simple installation. All indications are that the airlines will require a multiple waypoint storage capability in their area navigation equipment. Thus, a complete RNAV flight could be programmed into the system in advance. Think a moment about what the RNAV concept permits. A pilot can accurately fly parallel to a given route at a set distance. A pilot can be told to fly to a certain point off the airways, and he can fly there without radar vector help. A pilot can be told to hold over a given point, and he can hold precisely. A pilot can be told to fly a predetermined approach route with altitude requirements known for key waypoints, and he can do it. In every case, the pilot knows exactly where he is. This has been proved time and again by flight tests.
That's the beauty of area navigation. The pilot doesn't have to depend upon the controller to navigate his aircraft. All he needs to know is where the controller wants him to be. Then the pilot navigates to that point. There's no need for constant vectoring, communications are reduced, and the controllers are free to monitor traffic.
How will this area navigation capability be integrated into the national airspace system? Right now, planners are defining RNAV routes that will be used in addition to the present VOR route structure. They recognize that random routing of IFR traffic would lead to chaos. So instead, the routes will be carefully fixed. Route headings and locations of waypoints will be charted. This RNAV route structure will include such benefits as bypass routes for heavily congested areas, improved alignment of routes, eliminating doglegs, Multiple routes, so traffic can be segregated by speed or other operating characteristics. Dual routes for one-way traffic. Optimum location of holding patterns. More airport instrument approach capability. Pilot navigation of commonly flown radar vector paths, and special routes and procedures for STOL and helicopter operations. Since the area navigation concept relies on airborne equipment, these benefits can be achieved without adding ground facilities. Now, what does all this mean to the controller? For the en route situation, the advantages are immediately obvious. The addition of a fixed RNAV route structure will mean greater flexibility for the controller.
Eastern 139.
One-way RNAV routes will mean a greater number of aircraft can be moved en route with less voice communication. High-speed aircraft can be cleared on separate routes, away from slower aircraft traveling on parallel paths. In cases where an overtaking situation occurs, the controller can simply contact one of the aircraft.
American 610, slower traffic ahead, turn right, heading 260 until 5 miles, offset right of J875 Romeo.
Then proceed 5 miles offset of J875 Romeo until further advised.
American 610, we have the traffic, and cleared to turn right heading 260 until 5 miles offset of J875 Romeo. Then proceed 5 miles offset right of J875 Romeo until further advised.
The pilot has the onboard capability to fly to a point 5 miles from his original course, and then to maintain a course parallel to his original heading. No radar vectoring is involved. The pilot can see exactly where he is relative to his original track. When the controller sees that the faster aircraft has moved ahead of the slower plane, he merely tells the pilot to turn back to his original course and continue on.
American 610, turn left heading 170, intercept J875 Romeo, and resume normal navigation.
Similar procedures can be used to move aircraft around severe weather when requested by the pilot. Instead of laborious vectoring, a flexible routing can be provided, and the pilot can navigate it himself. The controller need only radar monitor his progress.
United 170, turn 30 degrees left, intercept 10 miles offset course, proceed 10 miles offset left of J895 Romeo for 50 miles. Then turn 45 degrees right, intercept J895 Romeo, and resume normal navigation.
En route holding points can be pre-planned without the current restraints of nav aid location or course alignment. This permits greater flexibility in en route holding and increases the capacity of the system. The pilot, regardless of the type of RNAV display on board, can fly the holding pattern with great accuracy because he knows exactly where the holding point is and where he is relative to it. There's no doubt that the RNAV concept permits more efficient use of en route airspace. And as center controllers become more familiar with the system, they will find that more of their time will be spent monitoring the progress of RNAV traffic on their radar, and less time will be spent on radar vectoring and ground-to-air communications. In the terminal area situations, there are also many advantages to the RNAV system. Prescribed RNAV approach and departure routes can be flown by the pilot himself without the need for vectoring from the controller. This can greatly relieve the workload for both the pilot and the controller. For example, an RNAV approach route may have several feeder paths, each carefully charted and numbered. The controller merely assigns his approaching aircraft to one of the feeders, depending on its speed and its relationship to other traffic.
American 320, cleared for RNAV, runway 22, right approach.
Once assigned a route, the pilot enters the location of the waypoints, then flies his RNAV display.
Papa, turn right, heading
The controller
090,
monitors, making certain safe separation is maintained. Routine radar vectoring is greatly reduced or even eliminated.
King Air 246, cleared for Claypool 2, RNAV arrival.
to 133 VFR, 12 Southwest.
Multiple feeder paths were used at Chicago's O'Hare during the United and American flight tests and proved to be a tremendously flexible and useful approach procedure in that high-density area. The demonstrated accuracy of RNAV equipment permits route widths in and out of terminal areas to be reduced from 8 nautical miles in width to 4 nautical miles. Further width reductions may be expected on final approach for RNAV-equipped aircraft. AreaNavigation permits special descent and ascent paths for high-performance, high-altitude flights into terminal areas, helping eliminate some of the problems now created by these aircraft transiting altitudes. AreaNavigation also permits aircraft approaching or departing from satellite fields to proceed more directly on course, thus avoiding crowded nav aids in and around terminal areas. It permits better noise abatement approach and departure paths, independent of ground nav aid location. Obviously, the AreaNavigation concept permits more efficient management of the airspace around terminal areas, an especially important factor when available space is restricted because of adverse weather, icing, or turbulence. AreaNavigation also permits special arrival and departure routes for VTOL and STOL aircraft, a source of increasing pressure on the air traffic system. These aircraft can come and go on their frequent commuter runs with a minimum of disruption to the flow of higher performance aircraft. A third major application of AreaNavigation is in RNAV approaches to runways without instrument approach capability. The pilot enters the published location of an initial approach waypoint of the airport into the RNAV equipment. Then he simply flies to that point and begins a standard FAA-approved RNAV approach procedure. He may have an intermediate waypoint, a final approach waypoint, and a missed approach waypoint. His RNAV display shows him exactly where he is relative to each. He lets down just as he would if there were a non-precision approach at this location.
All of the present applications of the AreaNav method are a forecast of the day when vertical guidance will be incorporated into the system. Then a pilot will be able to program an entire flight from takeoff to touchdown. Like all AreaNav flights, it will be identified by one of these designations on the flight strip. It will take off on a predetermined departure route with altitude requirements entered into the system. By flying the AreaNav displays, the pilot will know he is at the correct altitude over a particular waypoint. This flight can continue without interruption, unless there is weather to be avoided or other traffic to be considered. In these cases, controllers monitoring the flight will give the necessary instructions to depart the course. The controller tells the pilot when he can resume his original course or clears him for a new course. The flight continues on to its destination with the pilot navigating from the cockpit. When it arrives at the airport, it makes its approach on one of several feeder paths assigned by approach control to achieve the most efficient arrival sequencing. Communications have been kept to a minimum. The pilot has been relieved of much cockpit workload. The controller has been freed of routine radar vectoring chores and has been monitoring the transit of the aircraft through his area. It sounds too good to be true, doesn't it? Well, believe me, it will be a big improvement when the system is fully in effect. Meanwhile, the big question is, what happens during the changeover? We cannot incorporate AreaNavigation into the system overnight, nor can we build the structure hastily. It's as if we were transitioning some years ago from the old low-frequency range system to our present VOR system. Our first priority will be in the transcontinental route structure. We will follow that with routes between city pairs and the establishment of AreaNav systems in the terminal areas. There will be a period of time that the number of AreaNav flights will be small. During this time, the controllers will be handling traffic in the system as usual, providing radar vectors for en route traffic and vectors for those aircraft in the terminal area as well. It's possible many of you will consider early AreaNav flights in the system a nuisance, aircraft that will cause more work for you rather than less. This is a problem that occurs during any transition period. However, the benefits of upgrading the present system to include AreaNavigation will very quickly offset any inconveniences during the changeover.
The RNAV system is deliberately designed to be compatible with the present NavAid system. For that reason, it is possible to change an aircraft having both capabilities from an en route RNAV route to a route in the present system, and vice versa. Flexibility is inherent in the system. AreaNavigation is an innovation that may be as important to air transportation, four-course radio navigation system to multiple-course VORs. It comes close to giving us the capability for establishing instant airways anywhere. AreaNavigation is a big step forward in making the national airspace system more efficient while retaining the same high level of safety.
Radar contact,